Hello, welcome to week 3 lecture 1. In this week we will introduce public key cryptosystems or asymmetric ciphers. Of course, the first question that comes to mind is that what are public key cryptosystems and what is symmetry and asymmetry in a cipher. Now, for that let us think of what we have done already. Now, we have been looking at situations where Alice, the sender, wants to send a message to Bob. Now, what Alice does is that she chooses a key from the key space and transmits to Bob by a secret channel and once this key exchange takes place, after that Alice uses the encryption function to encrypt the messages or plain text and sends to Bob. Bob uses decryption function corresponding to the key on the encryption function applied on the message to get back X. So, this is what happens. Now, if we look a little more closely, we will see that in a way there is a symmetry of the knowledge or a symmetry on the knowledge that is shared by Alice and Bob. The secret that they shared together has a symmetric property in the sense that they know the same thing essentially, because of course they have to exchange a secret key which is not known to all, only Alice and Bob knows. Now, suppose instead of giving Alice the key, suppose Bob kept the key to himself and gave Alice only this encryption function, but then the type of ciphers that we have seen so far, they are the knowledge of encryption function will let Alice know the decryption function without any difficulty. For example, if Alice and Bob are using a shift cipher, then of course, I mean it is just the key is something between 1 and 25 and you have to just take minus of that key and reduce modulo 26 and then Alice will know the decryption function. And it's similarly for affine functions and for other functions, and then we will see the block ciphers that we have studied. There also the keys encryption key and decryption keys are kind of interchangeable in the sense that if somebody knows the encryption key, he will be able to know the decryption key and vice versa. So, that is the symmetry that we have in symmetric ciphers. So, these are called private key cryptosystems or symmetric ciphers. Now, there is a problem with symmetric ciphers. It is like this. Suppose that Bob has to communicate to several people and those people need not have had a secret channel with Bob so that they could have communicated the secret key. Then what will Bob do? So, it was proposed somewhere around 1976 by Diffie and Hellman that something can be done here, that probably Bob can publish a key, or let us say an encryption function, into public such that anybody who would like to communicate to Bob will use this encryption function and send in the message. Like someone, let us say this is A1, then let us say A2 is sending a message like this, let us say A2 is sending X2 and like that. But this encryption function will be such that knowledge of encryption function does not let the person with that knowledge the ability to compute the decryption function. Then if he knows the encryption function, the whole construction should be such that the computation of the decryption function becomes infeasible. If that happens, then we will have something that will be called a public key cryptosystem or an asymmetric cryptosystem, where the asymmetry is with respect to the knowledge of the sender and the receiver. That is, the sender does not even if the sender knows the encryption function, she is unable to know the decryption function. So, there is an asymmetry, although the receiver knows both, because of course, because the encryption function is publicly available and the decryption function is a special knowledge that the receiver has. So, it is called public key cryptosystem. Or asymmetric ciphers. Well, then the question occurred to people is that, well, as an idea it is good, but are there efficient and algorithms which for public key cryptosystems? And that was designed just 1 year after the publication of Diffie-Hellman's idea in 1977 by Rivest, Shamir and Edelman, and they designed something which is called the Rivest, Shamir, Edelman cryptosystem, or RSA cryptosystem in short, and this is what it is. So, the idea of public key cryptography was proposed by Diffie and Hellman in 1976. By the way, although it is known today that this was known possibly in late 60s by the British and American intelligence agencies, but it was kept confidential. But in academics, the idea of public key cryptography was proposed by Diffie and Hellman, and just 1 year after that, Rivest, Shamir and Edelman proposed the RSA cryptosystem, which is a practical implementation of the idea. Now, we will move on to RSA cryptosystem, and these are the details of RSA cryptosystem. Now, let us explain this cryptosystem stepwise. In the first step, we need two large primes. So, two large primes, let us call the primes P and Q, and then we will take the product of these two primes and we will get a number which is n. So, that is what I have written in the first line. And now, of course, we are talking about cryptosystems. So, the question is, what is the set of plain text, what is the set of cipher text, and what is the set of keys? The set of plain text, script P and the set of ciphertexts script C both are same and equal to Z sub n, that is the integers modulo n. So, we have P, we have C, which is equal to Z sub n, where n is equal to P and Q, and now we come to keys. Now, interestingly here, the key is consists of a n, which is the product of two primes, and the primes themselves. So, a single key for this cipher will consist of this n, and the primes which make up this key make up this n, and after that there are some other numbers. So, one number is B, and B is chosen at random from Z sub n with the property that GCD of B and phi n is equal to 1, where phi n is equal to P minus 1 into Q minus 1. Just little afterwards we will be talking about phi n in more details, and we will say that what really phi n is, but right now we are not doing that. So, just remember that phi n is P minus 1 into Q minus 1, and then we also know from our previous lectures that on modular arithmetic that if B is co-prime to phi n, that is GCD is 1, then it is possible to find A, that is there exists A belonging to Z sub n such that A times B is congruent to 1 modulo phi n, and this is the last component of the key. So, they together have to follow this condition A into B is 1 mod phi n. We will look at the computational issues soon, not now. Let us say we can do this. Now, so once we have this key is split up into two parts. One part is called the private key, the other part is called public key. Now, let us remove some of the writings from the board and write the key at the top. So, I have a key like this is a total key. So, this is N, P, Q, A and B, and these two elements make up the public key and the rest P, Q and A make up the private key. What is claimed and what has not been disproved so far is that if someone knows N and B, and if P and Q are very large primes, possibly having a representation of more than 600 bits long, then knowing n and b does not let anyone to compute the factorization, and hence the inverse modulo phi n in a in feasible time, in a reasonable time. So, it is computationally infeasible for anyone to compute A given B and N without the knowledge of P, Q or phi n. So, this is something, a claim on which RSA cryptosystem rests, and the security of RSA cryptosystem depends, and nobody has been able to disprove this claim. So, now we come to the encryption and decryption of RSA. The encryption of RSA is done by using the public key, which is N and B, so the encryption function EKX is equal to x to the power b mod n, and the decryption function is dk y is equal to y raised to the power a mod n. Now, let us look at a small example of RSA. Of course, in practice it is not secure with so small parameters, but let us check that what happens. So, what we are going to do now is to choose P and Q as particular primes. So, suppose P is 13 and Q is 17, both are primes, and therefore, let me modify my writings here. So, P is 13 and Q is 17, and therefore, the product is 221, and phi n is equal to 13 minus 1, 17 minus 1, this is equal to 192. We can check this. And now we have to choose B, which is co-prime to 192. A note of caution, B is co-prime to phi n and not n. So, if we choose B in that way, B equal to 55 will work, and once we have B equal to 55, we can essentially use the technique that we have discussed again in our previous lectures from week 1 onward, that I can compute the inverse of B modulo 192, and for that I do not have to do searching. I can use Euclidean algorithm in back and forth and get the inverse. I have discussed that, and in this case this inverse is going to be 7. So, we can check that 7 into 55 is equal to 1 or congruent to 1 mod 192. We have this, and now we have a setup over here, and so we know that B is 5, and if B is 5, A is going to be 7, and therefore we have the key that is going to be as you see here 221, 13, 17, 7 and 55. So this is RSA parameter generation, and once we have generated the parameter, we can do the encryption. So for that, let us take again an example of the plain text. We have told that plain text is Z sub 221. So plain text in this case can be any number from 0 to 220. So we choose a number 128. I am deliberately choosing 128 because I want to show that it need not be the number that we choose need not be co-prime to n, and sorry, yeah, no, it's something different. What I want to show is that the number that we choose, it need not be co-prime to phi n, it can be any number. If we take any number in Z sub 221, so in this case x equal to 128, and we raise it to the power 55, and then we will see we can do it by calculator so far. So we will see that modulo 221 is going to be 2. So that is my encrypted value, and if on the other hand we take the encrypted value and raise it to the power a, then reduce modulo 221, it is trivial to check that we are going to get 128 because 2 raised to the power 7 is 128. So at least for one instance we see that the encryption and decryption works. Now we have a question that will encryption and decryption for RSA work for all instances? For that we have to show that given any x inside Z sub n, if I raise it to the power a, I am sorry, first raise it to the power b, and I take mod n, all right, and then I raise it to the power a, x to the power b mod n, raise it to the power a, then again take mod n, this is going to be x to the power a into b mod n, and I want to show that it is equal to x always. Now in order to show, we need to show this to show that the RSA is indeed a valid crypto system. Of course it is a valid crypto system. So in order to prove that, we have to know a little more about phi m. Now phi m essentially is a number of positive integers starting from 1 to m minus 1 which are co-prime to m. So we have written the definition of phi m at the first point, and then the question occurs how to compute phi m. At this point we cannot discuss the details of the proof of the expression for phi m, but it is not difficult to remember. We will remember that phi m is equal to m times 1 minus 1 by p1 into 1 minus 1 by p2 and so on up to 1 minus 1 by pn, where pi's are the prime factors of m. Once we remember this, we move forward, we come over here. Eventually what we would like to prove here, and that is what we have to remember, is this. Let me write it down separately. Give me any number, any integer A such that the greatest common divisor of A and M, where M is a positive integer, this should be 1, then A raised to the power phi m is congruent to 1 mod m. Now, this is a general rule. Now, I have written the outline of the proof here. To go through the outline, it's mainly like this, that I can list down all the positive integers in Zm which are co-prime to m, like this x1 up to xm, and then if I take an integer co-prime to m and multiply all these xi's by that integer a and then reduce modulo m, then I will be getting all the distinct xi's one by one in certain order. So, essentially it is not difficult to see that we will be getting all the distinct one, even if we multiply them by a and reduce modulo m. We do that, and since a and all the xi's are eventually co-prime to m, if I take the product, they are going to be equal modulo m. If I do that, after that the left hand side can be transposed to the right hand side, and a raised to the power phi m minus 1 factors out. We have a raised to the power phi n minus 1 in one side, product with the product of all xi's, and that is going to be 0 mod m. And we have started with the assumption that xi's are co-prime to m, so their product is not going to be divisible by m. Therefore, a raised to the power phi m minus 1 is going to be divisible by m, and therefore we have this ultimate thing, and we are not to forget this m. Now, particularly there is a special case if m is equal to p a prime, then a raised to the power p minus 1 is congruent to 1 mod p, because phi p is equal to 1 minus is equal to p minus 1 if p is a prime. So, we have this. Now, we are in a position to verify the invertibility of encryption and decryption function of RSA. So, we have come over here. So, in the first line, let us see, we see that a b are inverse of each other modulo phi n. So, I can write a b equal to t times phi n plus 1, and then I choose x inside z sub n or z sub p q such that in the beginning x is co-prime to n. Now, if x is co-prime to n, then we know that x raised to the power a b is equal to x raised to the power t times phi n plus 1 is equal to x raised to the power phi n raised to the power t into x. Now, since x is co-prime to n, x raised to the power phi n is going to be equal to 1 mod n, and therefore this portion is 1 and then I am going to get x mod n. So, at least if x is co-prime to n, we have proved that the encryption and decryption are inverse of each other. We have the last portion here. Suppose x is not co-prime to n, then what is going to happen? Now, it is not difficult to see that since x is between 1 and pq minus 1, x cannot be divisible by both p and q. So, either x is divisible by p or x is divisible by q. We assume that x is divisible by q and not divisible by p, and q is prime. Therefore, greatest common divisor of x and q not equal to 1 and x divisible by q, they are same things. So, we have got this, and x is not divisible by p. Now, since x is not divisible by p, we know that x raised to the power p minus 1 is congruent to 1 mod p, which implies that x raised to the power p minus 1 into q minus 1 into t plus 1 is congruent to x mod p. And well, once I have here, we have already assumed that x is divisible by q, and therefore both these sides are divisible by q. Therefore, I have got this condition free of cost. So, I have got x raised to the power p minus 1 into q minus 1 into t plus 1 is congruent to x mod q. And now we have a scenario where p divides something minus x and q divides something minus x, the same thing, and p q are primes, therefore p q divides that. So, therefore, we can ultimately write that x to the power a b, which is equal to x to the power p minus 1 into q minus 1 into t plus 1 is congruent to x mod p q, which is equal to x mod n. So, this verifies the RSA algorithm. So, we can sum up now. We have introduced the idea of public key cryptography, public key cryptosystems, and we have described the RSA algorithm. So, that is end of today's lecture. Thank you.